High above the air we breathe, at the boundary of a new frontier, journey with us to the edge of space, right now, on Nova.
Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. The Corporation for Public Broadcasting. And by contributions to your PBS station from viewers like you. Thank you. Additional funding from Roger and Vicki Sant.
On a stormy night in Denver, a team of scientists takes to the air to investigate a mystery.
I reported it, and nobody had believed me.
They're trying to catch a burst of energy so fleeting and hard to see that scientists call it by the ethereal name of Sprite.
The bolts that cause sprites are super bolts, the kind of lightning that will blow your TV sky high.
Unlike the brilliant northern lights created in the upper atmosphere by streams of charged solar particles, sprites are high-altitude sparks that originate right here on Earth. They're leading researchers on a chase into the far reaches of the upper atmosphere to a little explored region, home to many mysterious phenomena. Earth's atmosphere is a thin blanket of gas. The troposphere is the lowest and densest layer. All of life as we know it depends on this relatively thin, 5 to 10 mile thick band of protective air. Its thickness varies with latitude and the seasons. This is where most weather occurs, including the towering thunderclouds that generate lightning. A high-altitude helium-filled balloon ascends quickly through this region and enters the stratosphere, where most jet planes fly, and where the ozone layer is found, which absorbs the sun's ultraviolet light that can damage living things. Moving into this hostile environment, the air pressure drops, causing the balloon to expand. Up here, the lack of oxygen would quickly kill a person. The stratosphere reaches an altitude of about 30 miles. Eventually, the balloon cannot rise any higher. But the ever-thinning upper atmosphere, including the ionosphere, extends another 500 to 600 miles, even beyond the orbital height of the International Space Station, which circles Earth at an altitude of between 200 and 270 miles. From here, the ISS looks down on the planet. The ISS is an ideal platform to study the edge of space, thanks to the cupola observation window. It offers a priceless view of space and the planet below. Its heavy shutters open to reveal windows for photography and viewing. The team also successfully captured a sprite from different angles, as they had originally planned, using high-speed cameras placed on the two aircraft. By combining the images from the two cameras, the three-dimensional structure of the sprite becomes apparent. A large number of electrons collide with the atmosphere, creating brilliant bursts of light and opening channels where the electrons can flow. Each sprite channel can be hundreds of yards wide. A sprite event is like a switch that turns on an electric current in the space between the Earth and the ionosphere. In fact, Our planet is surrounded by electric current, from the surface to the edge of space. Like lightning, sprites help to complete a global circuit, allowing charge to flow continuously around the Earth. But sprites reach much farther than lightning. And unlike lightning, sprites can transfer charge into the ionosphere, to the edge of space. Not only that, but the bolts of lightning that create the sprites are so powerful that they literally reverberate around the world.
When a sprite occurs, the parent lightning that causes the sprite radiates electromagnetic waves. Those waves propagate in what we call the global circuit.
Earl Williams of MIT studies sprites from this remote laboratory in western Rhode Island. Williams and his equipment are nearly off the grid out here, but they're completely plugged into the biggest circuit of all, the global electric circuit.
We've been monitoring this phenomenon for nearly 2 decades at this site, trying to look for long-term trends.
In fact, scientists have actually been measuring the global electric circuit on this unusual site since the 1950s, when the lab was set up by Williams' predecessor, Charles Polk, of the University of Rhode Island.
The antenna immediately behind me is Charles Polk's. The more distant antenna is one that we constructed when Polk's antenna was struck by lightning and blew the antenna into many separate fragments all over the meadow we're sitting in right now.
Williams got involved with early sprite research by collaborating with Walt Lyons of the Yucca Ridge Field Station.
Every time Walt saw a sprite in Colorado, which is roughly 2,000 miles from here, we would see a big disturbance here in Rhode Island.
The antenna Williams is using measures a very low-frequency wave, like a steady hum, that resonates between the Earth and the ionosphere.
When a sprite occurs, the lightning that causes the sprite sends waves in that thin cavity around the world 2 or 3 times. And it is exciting something called the Schumann resonances. And the Schumann resonances is a manifestation of what we call the AC global circuit.
Earl's aunt was a prominent violin player, so it's not too surprising that he thinks of it in musical terms.
The vibration of a violin string is very much like what happens with Schumann resonances. We have a fixed string length, and there's one wave on the string which has a fixed frequency, say the A note of 440 hertz. For Schumann resonance, we have a fixed length, but the length wraps itself around the world. And for that fixed length and the speed of light, we have a fixed frequency of 8 cycles per second. So they're both examples of resonances, this one being a mechanical resonance, that one being an electromagnetic resonance, but the same wave phenomena applies.
It's almost like the music of the spheres, or of the Earth at least.
No matter where you are on Earth, if you have an antenna, a vertical antenna, like the one behind me, you will see an oscillation on that antenna at roughly 8 cycles per second. And that is maintained continuously by all the lightning on the planet. Every time there's a lightning flash, a small fraction of the energy in that lightning flash feeds into this global resonance.
The Schumann resonance is present all the time. It never dissipates, because there's always lightning someplace on Earth. And when a sprite is produced by a superbolt of lightning, there is a spike in the Schumann resonance signal.
Every sprite lightning is a bell ringer for the Schumann resonances. One of these giant lightnings will single-handedly excite the whole Schumann cavity with electromagnetic waves. And everyone on Earth who has a receiver in the range of frequency of 8 cycles per second will detect a sprite event. Here on the oscilloscope, we have an example of the Schumann resonance signals. You can see the characteristic 8 cycle per second oscillation continuously. That's called the background Schumann resonances. Occasionally, you'll see a big increase in the amplitudes. Those events are the events that make the sprites. These are the lightning flashes, the very energetic lightning flashes that create sprites in the thin upper atmosphere.